Hello and good day again everybody, welcome again to Engineering Physics, and for today's video we would now be discussing about rotating bodies. So in rotating bodies, what does rotation mean? So when we say rotation, it is basically the movement in a circle about a fixed point. So suppose that we would be having this diameter. So let's say that this is once again the diameter of a circle. And in this diameter, let's say that its center is approximately here. So let's say that this is now to be its center. So if this is now to be the diameter, so this is now to be the radius, and this is now to be the radius because the radius is to be half the diameter. So once again, let's suppose that this is now to be the diameter. So in rotating bodies, so once again, it is now to be the circular motion about a fixed point. And in this example, the fixed point is now to be the center. So if that is now to be the case, and we would now be rotating this, so it would now look like this. So in a nutshell, this is what rotation looks like. So once again, angular motion or circular motion. Okay, so in linear motions, I will just be writing at the bottom part. So in linear motion, of course, the motion is along a line. And in rectilinear motion, the motion is now to be in a straight line. So suppose that this is now to be the motion. And let's say that a certain particle has an initial position here and has a final position here. So if that is now to be the case, the displacement here, so displacement, is now measured linearly from the first position up until the final position. So this is now to be in terms of meters, in feet, as long as it is now to be a linear measurement. So once again, this is now to be your delta x or the displacement. That is just for linear motion. What about for rotating bodies or in circular motion? So if this is now to be the motion of your object, when we are to measure its displacement, it is now to be in terms of angle. So in here, linear motion, its displacement is to be in terms of linear measurement. And in angular motion, its displacement is now to be in angular measurement. Suppose that this is now to be a radii. And if we would now be rotating it, let's say counterclockwise, so it would now look like this. So in this case, the angle or the displacement here is basically this particular angle. So there, so this is now to be the displacement delta angle. So suppose that this is now to be our final angle and this is now to be our initial angle. So let's say that this is now to be 45 degrees, for example. And for theta I, let's say that this is now to be 0 degrees. So for you to get the angular displacement, this is basically equal to, so final minus initial, and this is equal to 45 degrees minus 0 degrees. So it would be as simple as that. Oh, by the way, answer. So 45 degrees. So this is now to be the angular displacement at this position. However, in rotating bodies, we are not only concerned with degrees, because as you know from your lower year subjects, we also know that there is to be the presence of radians, or there is this thing which we call radians, I should say. So in degrees, as you have learned in your high school and elementary years, so in degrees, this is now to be a sexagesimal unit. So sexagesimal. So when we say sexagesimal, its base unit is now to be in terms of 60. And we can say, once again, from our lower subjects, that one rotation, so one rotation for a circle, is to be equal to 360 degrees. So this is for one rotation. So for half rotation, this is now to be 180 degrees. And for 1/4 rotation, this is now to be 90 degrees, 1/8, 45 degrees, and etc. So suppose that this is once again to be the diameter of our circle. And if I am to rotate it, so as you can see, there is now to be the angle there if you can zoom in the video. So this is now to be 0 degrees. So 5 degrees. This is now to be 20 degrees. So this is now to be 90 degrees, 180 degrees, 270 degrees, and 360 degrees. So once again, one rotation is to be equal to 360 degrees. But what about in radians? So in radians, so our angle in terms of radians is basically equal to the arc subtended by the circle, or let's say by that angle divided by the radius. Okay, so let's say that we would be having this particular circle on the left. So let's say that this is now to be your angle theta. So once again, let's say that this is now to be your angle theta. And if that is now to be the angle theta, this is now to be the arc subtended by the angle. So at this particular portion. So that is now to be S, and this is now to be R. So this is now to be the arc subtended, and this is now to be the radius. So just divide the arc subtended by the radius. Okay, so what is now to be the radians in one full rotation? So by the way, so one rotation is to be equal to how many radians? Okay, so let us solve for it using this equation. So the angle in radians, so that is now to be equal to, so what is to be the arc subtended by one full rotation? So what that means here is that, so if I would now be redrawing our figure to the left, so if this is now to be the diameter, and for the angle, so from the 0 degree line, you would now be going one full rotation. So in other words, in sexagesimal units, that is once again 360 degrees. So with that, the arc subtended by one full rotation is basically the circumference, which is the whole of the circle. And if you can remember, that circumference is basically the perimeter of a circle, and circumference is, circumference can be solved by the equation 2 pi radius. Okay, so take note of this, that the circumference is equal to 2 pi r. Okay, so with that, if this is now to be the arc subtended by one full rotation, which is the circumference, so that is now to be equal to 2 pi r. So that is just for your s. So we would now be dividing this by r. So with that, r would now cancel out, and we can now say that the angle in radians for one full rotation is equal to 2 pi. So once again, 2 pi is now to be the angle in radians for one full rotation. Okay, so take note of this. So the angle in one full rotation in sexagesimal units is now to be 360 degrees, and the angle in radians is now to be in 2 pi radians. So its unit is now to be in radians. So we can now conclude that 2 pi radians is equal to 360 degrees. So if you would now be converting from radians to degrees, so this is now to be our conversion factor, and of course, vice versa. So once again, both of these values are for one full rotation. Okay, so suppose that we will be converting from 45 degrees. So let's say that your angle is now to be 45 degrees, and we want to convert it in radians. So how can we how can we convert this to radians? So we would just be making use of this conversion factor. Okay, so with that, so 45 degrees. So what I am going to do here is that I will be multiplying this by my conversion factor. And this is now to be, so for our conversion factor, I want degrees here to cancel out. So I would be writing degrees at the bottom part and radians at the upper part for me to arrive at an answer in terms of radians. So how many degrees are there in a certain radian? So as per this equation here, there are 360 degrees for every 2 pi radians. So degrees would cancel out, and once again would leave us an answer in terms of radians. So looking at the calculator to your left, that is now to be equal to, so 45 times 2 pi, so 2 times pi, so 2 pi divided by 360. So basically, this is now to be 1/4 pi. Or if you want this to be in terms of decimal, so its answer would now be equal to 0.7854 radians. So this is now to be our answer if you want to convert 45 degrees in terms of radians. But what about if it is to be the other way around? So suppose that I want to convert pi over 2 into degrees. So same thing, so pi over 2 radians. So this is to be radians, by the way. So pi over 2 radians, multiply this by our conversion factor. And for us to arrive at a unit in degrees, so degrees would be at the upper part and radians would now be at the bottom part for radians to cancel. So once again, for every 360 degrees, there are 2 pi radians. So as for that, just multiply this. So looking at the calculator to your left, so pi over 2 times our conversion factor of 360 degrees divided by 2 pi. Okay, so equal sign. So this is basically 90 degrees. What we mean here is that pi over 2 is equal to 90 degrees. So what about for, let's say, 4.021 rads or radians? So let's say that I want it to be converted to degrees also. So same old, just multiply this conversion factor. That for every 360 degrees, there are 2 pi. There is 2 pi radians. So radians would cancel out. So with that, looking at the calculator once again, so 4.021 times 360 divided by 2 times pi. So this is now equal to 230.386 degrees. So there we have it. So this is now to be equivalent. So 230.386 degrees is to be equivalent to 4.021 radians. So there. Okay, so proceeding, since we already know how to convert degrees to radians and vice versa, let us now go back to our topic for rotational motion. So as a review, in linear motion, its position is now to be in terms of x. So you already know that. And if our position is now to be in terms of x, we can say that the displacement is now to be the change in position, thus delta x. So with that, for our velocity, this is now to be equal to, so for our velocity v, this is to be equal to the change in divided by the change in time. So this is for average velocity. For instantaneous velocity, that is to be the case wherein you would be getting the first derivative, etc. Okay, anyway, so for acceleration in linear motion, acceleration is to be equal to the change in velocity divided by the change in time. So acceleration basically is the rate of change of our velocity. Okay, so proceeding, so that is once again for linear motion, but what about for rotational motion? So in rotational motion, once again, for our position are to be in terms of angle theta. So with that, so our position here is now to be in terms of theta. So with that, for our displacement in rotational motion, this is basically change in angle. So change in angle. And for our velocity, in the velocity for rotation or the angular velocity, it is to be denoted by the Greek letter small case omega. So it would look like a W. So omega is equal to change in angle or the change in, well, position divided by the change in time. So delta angle, I should say, delta angle divided by delta t. So there. And as for acceleration, this is to be denoted by the small case Greek letter alpha. And this is to be equal to the change in angular velocity divided by the change in time, or the rate of change of our angular velocity. Okay, so considering all of this, if once again from linear motion, these are to be the equations that you have memorized before. So for rotational motion, what we would just be doing is that we would now be changing these symbols. However, we would just be making use of this very basic equations here. So what I mean here is that once again, from linear motion, your position is now to be in terms of x, and in rotational motion, our position is now to be in terms of theta. So let us just change x to theta. So theta is basically equal to, so what is once again the velocity in angle? So our angle in velocity, our velocity in angle, I should say, is now to be in terms of omega. So with such, this is just basically the initial omega plus the final omega divided by 2 times time. So it is to be this one here. And as for the second equation, so the final omega is equal to the initial omega plus what is now to be the acceleration in rotational motion. So that is to be alpha t. So there, and as for this, so this is now to be theta is equal to omega I times t. So I have, what I did here is just that I have changed x into theta and I have changed vi into omega I. So plus 1/2 alpha t squared. So this is for acceleration here. This is for equation number 3. So for equation number 4, so theta is equal to omega ft minus 1/2 times acceleration t squared. Okay, so as for this one, so this is to be, this is basically omega f squared is equal to omega I squared plus 2 alpha theta. So these are now to be the equations that we would now be making use in rotating bodies. So there.